Okay, so we're trying to break down some information about functions. So let's think about what we know. First, we talked about what makes something a function. Then we talked about domain and range, what x's work that you can plug in, what f of x's come out. We looked at intercepts. So now we're talking about even and odd, okay? Symmetry. What makes a function even or odd? So the first thing that we want to talk about is an even function. And so if we plug negative x into an even function, it goes and looks right back the way that it used to do. Now, why is that? Well, that's because it has what's called y-axis symmetry. So you can always tell an even function because you can fold it like a butterfly down the center. Think of the y-axis as the center of the butterfly, and you can fold it and the wings line up. So if we think about this being the middle of the butterfly, we can fold the symmetry up, and so it has y-axis symmetry. So if there is a point x, y on the graph for an even function, this will also have the point negative xy on the graph. Because if I stick negative x in to the function, it doesn't do anything. It doesn't change it. So there's a point over here that will be at the same height as over here, okay? So it's important that we know how to recognize it graphically. It's important that we need to know how to recognize it algebraically. So like if we see f of x equals x squared is what's pictured. It's an even function. It just so happens that it has an even exponent. That's not completely coincidence. Even exponents take a negative and makes it into a positive. So we can test it out. If we stick in negative x, we still get negative x squared, which becomes x squared again. So it doesn't hurt anything. It doesn't change anything. So if we plug in 1, we get 1. If we plug in negative 1, we also get 1. So there's lots of ways to think about it. But a even function has y-axis symmetry, and all of these algebraic and graphical things go together. Because you'll notice, as we've been exploring 1, 1, and 1, 2, we've talked about how the graph and the algebras go together. Okay, now let's talk about an odd function. An odd function has what's called origin symmetry. So what I think of origin symmetry is I can put a push pin in the center, and like it's a pinwheel, I can spin it 180 degrees, and it will look exactly like when I started. So I think of sticking a pin in the middle, and if I rotate it 180 degrees, there's no change. You can also think of it as a flip over the y, flip over the x. That's another way to think about it. So if we have the point xy in an odd function, we will have the point negative x, negative y. So the x value flips, the y value also flips. So this ends up being the opposite of f of x. So interestingly enough, and one example of an odd function, which is the picture I put in, is the cubic function. Now, not all cubic functions and not all quadratics are even or odd. The original parent function, x squared, is even. The x cubed function is odd. As soon as you start adding other terms, it might mess it up. But if you plug in negative x, you get negative x cubed, which is negative x cubed, which is the opposite of the original. So I think about this as the same as our original. And if you stick in negative x here, you get the opposite of the original. So you can see that here. If I stick in positive x or negative x, get the same y value. If I stick in positive x, I get y, but if I stick in negative x, I get the opposite. I get opposite of that. So this is just another way to classify a particular function. If it has y-axis symmetry, we call it even. If it has origin symmetry, we call it odd. So checking your algebra can be one way to do it. And then if you stick that function into Desmos and you look at the graph, does it have the property that I can fold it across the y-axis? Does it have the property that goes through the origin, or this piece is mirrored down here? So if there's a piece here, it would be mirrored down here. So it just goes, it doesn't have to go through the origin. There are pieces where you have a mirror here and here, and it never touches the origin. But it's called origin symmetry because if it was a sheet of paper and you rotated it around that origin, you could get what you started with. Okay, so those are just some definitions, some new terminology. So let's look at it by a graph, and then let's look at it algebraically. So in example, I don't know where we jumped to 5, but how about we go number 1? In this example, we have 3 graphs. We are trying to determine, are they even or odd based upon their symmetry? Are there any that look as if we could fold them over the y-axis and there's a matching piece on both sides? Yes.
The middle one.
Which one?
The middle one.
The middle one. So this is considered an even function. It has y-axis symmetry because we can fold it down this line. For every value to the left of the line, there's an exact matching value to the right of that line. So think about like being the bottom wings of a butterfly, okay? Are there any functions we see that kind of have a matching piece in one quadrant, and then if we flip it across the x and the y, it gets down to the opposite quadrant and goes through the origin? Do we have any like that? Do we have any that appear to be odd? We could put a push pin in the center, and then we could rotate it, and it would still not change it.
The one on the right?
Yes, this one right here. It does happen to go through it. Here, if we look at this point right here, it is to the left just under -1 and up a half. And then we have an exact matching piece or point in that other right corner. Watch, when I made the x positive, the y became negative. I made the y negative, it became positive, and so on. So this is an example of an odd function that has origin symmetry. Our first problem, if we shifted it over and this piece right here was sitting at the origin, it would be origin symmetry. But it doesn't. It's not lined up anyway, so it's nothing special. So it has no symmetry that we are concerned about. It's not even. It doesn't. You can't fold it across the y-axis. It's not odd. We can't spin it at the origin. If I spun this at the origin 180 degrees, it would look totally upside down and weird. Okay, so that one has no symmetry. Now, in example 2. In that example, we do want to make sure that we can identify it algebraically, okay? Any questions on how to look at it in the graph? Okay, we good with that? Okay. So let's check it algebraically. Here's what we're checking for. Remember, if we stick in -x and it goes right back to the way it started, it's even. If we stick in -x and it becomes the opposite of what we see, then it is odd. And that would be like if we totally multiplied the function, the original function, by -1. Now, if we multiply this original function by -1, We know what the original looks like. It's that. But if we multiply by -1, there should be a negative in front of here and a positive in front of there. So that's what I mean by the opposite. We actually multiply by -1, okay? So that's what we're checking for. So what do we check for? Well, all we're going to do is plug in -x. We're going to reduce it down as much as we possibly can and see what happens. So it's going to be -x squared minus 2 times -x. And then you're just going to pretend like the original wasn't there, and you're going to reduce it down as much as possible. Here, the negative is going to become a positive. Here, 2 negatives are going to make a positive. Now, the easiest thing to check is even. Is it an exact match of the original? Is it an exact match of the original? No. So it's not even. We can rule that out if it doesn't go back to the original, okay? Is it the opposite of the original? Meaning, if I multiply through by -1, would I get what I see on the paper? If I multiplied everything in this equation by -1, I would get -x squared plus 2x. Is that what we see? No. So it's not odd either. Okay. So now let's take a second and look at the graph. It should not be foldable across the y-axis. It should not be spinnable at the origin. So if we go into Desmos, and if we type in the function was x squared minus 2x, it is kind of lopsided. See how here's the y-axis. You can't fold it there. It's not lined up perfectly with that. If I stuck a push pin at the point 0, 0 and spun at 180 degrees, the arms would be pointing downward. It wouldn't be anything good. So you can see it doesn't fit algebraically or graphically. Okay. Now let's go back and look at example B. Example 2b, we got to do the check. If I stick in -x, I get -x to the 4th minus 3 times -x to the 2nd. -x to the 4th, because we have 4 negatives multiplied together, would become a positive x to the 4th. -x to the 2nd becomes an x squared, multiplied by -3 is -3x squared. So the first thing you always ask yourself is, does it look like the original? Is it an exact match of the original now? Yes. Yeah. So it's even. We can stop. If it looks like the original, it is a function that is foldable over the x or over the y-axis. So let's go in and check in Desmos. So if we type in x to the power of 4 minus 3x squared, guess what? You could definitely fold that over the x-axis without a problem. It's kind of like butterfly-esque in a way, you know. If we think of that as the bottom wings of the butterfly, it's doing what it should be doing. So the graph and the algebra should always coincide. If not, one of them is wrong. Now, if you typed it correctly into Desmos, Desmos is a great way to check your work. Okay, next. We have a function here that is the absolute value of x. Does anybody know what the absolute value looks like? Anybody know from algebra class what an absolute value kind of generally looks like, that graph? Remember? Anybody remember? The absolute value, for the most part, if it's just the absolute value of x, looks like a v. Okay, so keep that in mind. It looks like a v. If we stick in -x, let's look at what happens. It is the opposite of the absolute value of negative. x. What does an absolute value do to a negative?
Makes it positive.
It makes it positive. So this is going to now flip to a regular plain x. We don't need a negative inside that absolute value if it's just on one term like that. So it's unnecessary. So we ask ourselves, does it fit the even model? Does it look exactly like the original? It's the original, so it's even. So let's check in Desmos. Is it something that is foldable across the x-axis? Well, if you stick in the negative absolute value of x, guess what you get? You get a v. The negative in front just flips it upside down, but it's still a v. We still could fold it across down the x-axis, like if we had a piece of paper that it was drawn on, we could fold it there, and it's a perfect match on both sides of the x-axis, or y-axis, okay? So again, the algebra and the geometry should always match up. Let's do another one. Let's stick in negative x. We get the opposite of x cubed plus the opposite of x. So you see where the original x was sitting, I stuck in a negative x in parentheses. If you cube a negative, does it stay negative or does it become a positive? If we cube a negative, 3 negatives multiply and give you a negative. So that is going to be negative x cubed. And then this back, a positive times a negative is a negative. Okay. So does it match the original? Is it what we saw originally? So that's an easy one to check. Does it match the original?
No.
No. There's negatives where negatives weren't. So it's not even. An even function, when I stick in negative x, will match the original. Okay, let's check, is it odd? If I multiply this equation, each piece by -1, this would become a negative, this would become a negative. Is it the opposite of the original? Yes. So this is odd. Remember, an even function, when you stick in negative x, looks just like the original. An odd function, when you stick in negative x, it's like you multiply the entire function by -1. It's exactly what happened. So this one should have origin symmetry. So if we go back to Desmos and we stick in x to the third plus x, oh, goes through the origin. There's a piece in the top right and the piece in the bottom left. If there's a piece in the first, there should be a piece in the third if it's an odd function. If there's a piece in the left side, second quadrant, there should be a piece in the fourth quadrant. They should go together like that. They don't have to go through the origin, but it's pretty common, okay? So your job is to work on these. The first 3, you're going to be just graphically saying if they're even, odd, or neither. The bottom 10, you are sticking in negative x to each of them and saying, did they look even or did they look odd? And then if you want to check your work as you go in Desmos to see if you're doing your algebra right, but I want to see these. I want to see the algebra. You're just sticking in negative x and seeing how does it change. If it goes right back to the way it originally looked, it's even. If it's like you multiplied every piece by -1, it's odd. If some get changed and some do not, it's neither. And you should be able to check them all in Desmos. Okay? Good? Okay. So work on some homework.